So now let's find the equation for the envelope. So we have a family of curves here. Y equals the tangents of phi times x, and minus 1/2. Here we have g, and here we're going to have x squared divided by v0 squared and cosine squared of phi. We can write this as an implicit equation, fxy and phi, right, equals to tangents of phi times x and minus 1/2. Let's write this like that. G over v0 squared, and here we're going to have x squared as well, and here 1 over the cosine. Let's write 1 over the cosine as 1 plus tangents squared of phi, and all of it minus y. And so the implicit equation, if we define this by fxy, then fxy equals 0. This implicit equation defines this family of curves. And in my video with coffee cup caustics, I actually proved that when we have this family of curves, right, whenever we have some family of curves, this curve and this curve and this curve, and we're looking for a curve that will be tangent to all of them, this envelope, then in my coffee cup caustics video, I proved that we actually, for this curve, we need to solve this system of equations. So this has to be equal to 0, and then df by the phi, by this free parameter x, y, and phi. So watch my video on the coffee cup caustics, also has to be equal to 0. So solving the system of equations, we derive the equation for the envelope, for the enveloping curve. And so let's do it here. So of course, let's compute the f by the phi here. So the derivative of the tangents is 1 over the cosine squared of phi. This is times x, of course. And then when we take the derivative of y with respect to phi, this is 0, and this term times 1, this is 0. So we need to have, so we're going to have minus 1/2, and here we have gx squared divided by v0, where we need to differentiate this tangents squared of phi. So it's going to be twice and tangents of phi, and then the derivative of the tangents is 1 over cosine squared of phi. And so this needs to be equal to 0. And so of course we can reduce these 2 from here and 2 from here, and we can divide by 1 over cosine squared. Supposing it's not 0, we can divide by this, and we can also divide by x here and here, so assuming that x is not 0. So the power here is getting reduced, and as a result, what we get here is that tangents of phi equals to so this is 1, so it has to be v0 squared divided by gx. This is tangents of phi here. And so now if we plug it into this equation that we had previously here, right? So what we have, that the equation for the envelope, let's write it. So plugging here into here this, then we see that this x is getting reduced. So we are getting v0 squared over g, v0 squared over g, and this term we're going to have minus 1/2. And here we have, again, gx squared over v0 times gx squared over v0, and times 1 plus, and then tangents squared. So it's going to be v0 squared over g, all of it squared over 1 over x squared. This is the equation for the curve for the envelope. So let's call this y again, and this is going to be our equation. So what we have here is that y equals, so when we take this, so we'll see that when we multiply it by x squared, then x squared is being reduced, right? And here we have, this is v0 squared. v0 squared is reduced here and here, so we're going to have, and this is half, so we're going to have v0 squared over g minus v0 squared over g divided by 2. So this term combined with these times all of that is just going to give us v0 squared divided by 2g. And then the other term here is minus g divided by 2 v0 squared x squared. And this is the equation for the envelope. And now let's go into Desmos and actually plot this. So when we go to Desmos here, so let's go here and plot this equation y equals, so it's going to be here as we said, it's going to be v0 squared, right? Oops, what have I done? v0 squared divided by 2g, and we have this 1 times, let's write it like this, 1 minus x divided. So let's go quickly again and see by what. So we can say here that when we take it out, so it's actually here, yeah, this is going to be this squared. So this is v0 squared over 2g, and here it's going to be 1 minus, and here we're going to have x actually divided by 2 v0 squared over g, all of it squared. This is just the range of y, I think, right? Hopefully I haven't done any mistake here so far. Let me check, like make really quick, check really quick. Yeah, it shouldn't be mistakes here. Okay, so let's go to Desmos and see. So when we're going back to Desmos here, so it's going to be x divided by essentially here the maximal range. So it's going to be dx, and all of it just this. That makes a lot of sense, and all of it squared. Yeah, that makes sense, because we see here that this is normalized, because at minus dx, yeah, it's actually makes a lot of sense. I should have figured it out right away, because this parabola has to be 0 at plus dx and minus dx, this maximal range, and the maximal height for y is this. Actually, this is actually dy exactly, right? This is a curve, and if we want it for y greater than 0, then we plot it like that, and that's our envelope. So what else remains to be seen here? Well, we can derive, actually we've derived the equation for this ellipse, but we can actually prove that this is a canonical ellipse. But you know what, we'll leave it for this video. It's enough if, for those of you who are interested, it can be easily shown from this parametric plot that this is, you know what, let's do it anyway. Let's go. I'm improvising here with you, so let's just go there and compute this. So actually, this can also be written. So this, we've defined the maximum range for y. So this is what we defined by dy. So we can write this. Let's change this just for sakes of convenience. We defined it as dy here. So we have this. And okay, we can go here and make it a little bit more sparse here if we change it to 9, right? Or let's change it to 0, 0, 1, or maybe even 3. Yeah, so we see those possible trajectories here. Should have been more symmetrical, right? And okay, let's turn off those red ones and just see this ellipse. So the equation of this ellipse that we have to write, so we have all the parameters here, and we found this envelope for all the possible trajectories. And what else I wanted to produce here? Let's derive the equation for the ellipse here. So if we go to what we have here, so it's v0 squared. Okay, so we have yeah. So basically, when we're going to combine v0 squared over g, and this is cosine of t sine of t, so it's going to be v0 squared. So let's go to here. So it's going to be the equation. It's going to be v0 squared over 2g, and this is going to be the sine of 2 theta. This is for the parametric ellipse. And for the other part, if we go here, then what we're going to have here, it's basically this same. So it's v0 squared sine squared over g, and the same expression minus half of it. So it's going to be just v0 squared over 2g, and what we had here there is just sine squared of theta, or of phi. Actually, it was phi. Okay, and so we can show that this is an ellipse. So for that, let's just take this outside, this is called this dy. So it's some scaling factor dy times this ellipse sine of 2 phi and sine square root of phi. Okay, and this is our x and this is our y. And let's see the canonical. Let's ignore this and suppose that we have this parametric equation: x sine of 2 phi and y is sine squared of phi. Okay, so what we see here that if we take y minus 1, then this is cosine squared minus the cosine squared of phi, which we can write as minus, and here we will write, so cosine squared can be written as 1, and here I think, so cosine of 2 theta is 2 cosine squared of theta minus 1, so so it's 1 plus cosine of 2 phi here divided by 2, and so we see that y minus 1 is minus half minus the cosine of 2 phi here divided by 2. So if we add now 1/2 here, so when we add here 1/2, then this is gone, right? And so we have y minus 1/2 equal to that, and we see that y minus 1/2, right, all of it times 2 is going to be minus cosine to phi squared. So this is squared plus x, which is sine of 2 phi squared, equals to 1. And that's the canonical ellipse. So this is the canonical ellipse, which is centered here at half, and this axis along the x is just goes from -1 to 1, and here this is just it's like dividing by the, so this can be written as x squared plus y minus 1/2 divided by 1 over the square root of 2, all of it squared, equals to 1. So that's this ellipse that we have seen in there. So I've just proved that this equation is the ellipse. So basically we've analyzed everything. So we found the maximal range, we found that this is for the angle of 45 degrees, we found that the vertex of the peak height of each of those parabolas in this family of curves is on this ellipse, and we found the envelope. So in terms of geometry and fully characterizing this problem and its invariance, so of course an invariant here is v0 squared, it's independent, so the magnitude of the velocity, it is proportional to energy. Of course the magnitude of the velocity is invariant, it's independent of the angle here. And yeah, so we've analyzed this problem thoroughly. So please tell me what you think. Thank you for watching, and please consider subscribing.